Welcome to a presentation for the virtual quality control robot titled the Lobster for the ELEC391 final project by Group Maracas. For a system demo, you can see our marshmallow grabbing robot finishing its process in less than 9 seconds for grabbing all 3 marshmallows and disposing them in the garbage chute. It's pretty fast. Going forward, we fulfill all the RCG requirements, and as for the constraints, we use maximum motors and encoders, and motors operate fine. We only use one Arduino Leonardo. We don't need any master components in our design. And for Professor Stockley's email, we're using as our own choice, we're using 1 channel power supply. And bearing these goals and 3 parameters in mind, we will talk about our complex and clever designs.
On the mechanical side, the first step we conducted was defining the workspace dimensions with an interactive 2D SolidWorks drawing. The workspace is fixed and the joints and arms rotate and move as the real model would. Thanks to this neat 2D simulation, we were able to experiment and quickly determine the optimal dimensions for the arm and the workspace, saving valuable time in calculating the inverse kinematics. From here, the SolidWorks model was created, as seen as the next slide, with a double shaft design and joints for more stability and to minimize the material used. A transparent base enclosure was designed to hold the PCB. Reduction gears were also used at the shoulder and the gripper to reduce the required torque and inertia. The next slide shows the full SolidWorks arm assembly. In the Simulation X model, only 3 gripper spur gears were imported into the Simulation X. The joints were replaced by cylinders in a single shaft design in order to keep the simulation time to a minimum. The gripper tips were replaced by straight cuboids as opposed to the SolidWorks curved claw tips. However, the length and intended position of each individual parts of the arm were approximated to be similar to the original part.
For the circuit schematic, we had a few clever designs. We had decoupling capacitors on each motor to reduce noise coming from the power supply. On top of that, we added optocouplers that will reduce noise coming in from the motor into the Arduino. So basically isolated the Arduino and the motors from each other by using optocouplers and reduce noise. On top of that, to reduce costs and use a 1-channel power supply, we added a voltage regulator to our circuit that took 25 volts input and output 5 volts that went into the Arduino itself. And bearing this in mind, we added fuse protection to protect our motors and Arduino from overcurrent on each motor and the Arduino itself. As you can see on this PCB layout, we had a very compact design, and we also had a heatsink to protect the voltage regulator from overheating, on top of including the Arduino board itself on the PCB.
Sorry. Yes, so for the forward and inverse kinematics of the control system, we did not have to write any code because, as Isabel explained in her mechanical part, using this 2D simulation model that we made, we were able to calculate the angles we needed for each of the marshmallows and the drop locations. So we were able to significantly cut down on the runtime and clock cycles. Next slide. This is the Simulink model that we used to kind of model the system altogether. Each of the motors, motor 1, 2, 3, 4, represent the joints. And as you can see, there are subsystems at the beginning, 1 separating into 4. I would like to explain these subsystems, and I think it's a really cool original design that we came up with. Next slide. So the first subsystem is what you see on the left. This is step functions that go from 1 to 0, and all of them have encoded times in them. When it switches from 1 to 0, as you can see on the right side, the switches that say if the signal coming is bigger than 1, go to the top, less than 1, less than 0, go to bottom, sorry, not 1, 0. By using this, we were able to put in the angles previously before actually, we were able to input the angles into MATLAB using variables, and then just simply changing 1 variable or 2, we were able to completely manipulate the transition times and the locations we wanted the arm to move into. Next slide. Now, another issue we ran into when we were trying to simulate was the arm knocking over marshmallows as it was trying to pick them up. So a clever solution that we came up with was that the issue was the arm was moving from a marshmallow. Let's say it picked up the first marshmallow, moved to the drop location for the 1, and then moving to marshmallow 2, it would take a diagonal path. So we decided we would add an intermediate step where it would first move horizontally and then move vertically. So using this, we were able to get a system where the arm never actually reaches towards a marshmallow in any horizontal movement and always moves vertically, making sure that we never knock over any marshmallows. Next slide.
Thank you for listening. Have a good day.